Okay.
And we'll give it about another minute or so.
So we have 1 hour or 45 minutes for me to.
Well, we'll try and wrap everything up on the hour. You know,
Okay.
the talk and the questions.
Okay. I threw a bunch of additional slides in here that are part of our standard marketing talk that have way too much information on them. So I'll probably build a blast through the last dozen or more slides really quickly.
Okay.
But yeah, there'll be more time spent on others.
Okay, cool. Well, you know, we're sort of just at 8 o'clock. Welcome everyone. It's a real pleasure to have Cory Fehr with us this morning. And Cory is the founder of Integrity Insitu, and he's the inventor of the patented Insight tool technology. And he's been involved in business since he was 14 years old, and he grew up in an entrepreneurial home, and through all of this, he led, managed, and owned 4 different companies. And through all this, has been in the oil patch for 23 years, and he has background in computing, in reservoir engineering, geology, and project management. And he has a family of 4 boys. And he's been the subject of interviews on many occasions, numerous presentations, and he's grown his company from a 1-man effort to a 13-person team, and that's been in very difficult business environments, as we all can attest to. And Mr. Fehr holds the PMP designation, and he claims that his only weakness is that he spends too much time on LinkedIn. So, ladies and gentlemen, let's welcome Cory Fehr.
Good morning, everybody. Thanks so much for joining us. Please join me in recognizing and thanking John and Maricel and Nagel, specifically, along with the entire ARMA team, for hosting us and enabling these wonderful educational and networking opportunities. I really appreciate you guys thinking of us and allowing us to present. Today's discussion will briefly look at the changes seen in geomechanics over the years, ranging from ongoing modifications to formulas. I didn't actually get too far down that path when it came to the presentation material. Sorry, I just kind of lost my mouse on the screen. Applications of the discipline, of course, around the world, some of the technologies being used to acquire this critical information. My view on it all from an entrepreneurial standpoint, that is definitely going to take us down a few rabbit holes, and a bit of engineering discussion as well. So thank you once again for your interest. Now, Integrity Insitu, most people don't know this name, so I like to show this slide, and I am guessing that 95% of you have never heard of Integrity Insitu. So if that is the case, you'll be surprised to hear that we've been around for over 8 years, plugging away on various aspects of our patented Insitu geomechanics testing technology. We've grown to the team of 13, as John mentioned, which has largely occurred over the past 3 years. And as you can infer by the size of some of the foreheads you see on the screen, we've got a lot of experience. We've got over 300 years of experience with various aspects of technology development. Based here in Calgary, we have an office in Houston as well, and are planning to continue that growth this year. So this is our lovely team. Where and when did we first begin to experience geomechanics? Well, which do you suppose came first, mining engineering or civil engineering? Well, civil engineering, which until more recent times was synonymous with architecture, began to appear in ancient Egypt, Iraq, and the Indus Valley between 4000 and 2000 BC. Evidence from a South African coal mine dates it as being somewhere between 20,000 and 40,000 years old. Observing cave-ins and slope stability may have been our first insights into what is at different times being called geotechnology, geotechnical engineering, geological engineering, or geomechanics. Early mining practices seemed far from worried about the geomechanical processes that they were dealing with, and some would say that this is still the case unless a fatality or costly ore sterilization event grabs management by the collar. To be fair, other geomechanically coupled industries have also suffered greatly. One infamous example being the failure of the St. Francis Dam, in California in 1928. Regardless of the reasons for not performing the work, the lack of a geological examination of the dam site, including, of course, geomechanical assessment, is what was ultimately blamed for the loss of 426 human lives. Oil and gas has also had its share of geomechanical black eyes, although not generally causing a loss of life. Dating back 300 plus years, the formal arrangements of what we've come to know as geomechanics were beginning to take shape. The year was 1717, and French royal engineer Henry Gautier was annoyed. He was annoyed by retaining walls that leaned over after a long enough period of time, and damn it, he wanted a better method for calculating earth pressure. He did just that, and in 1729, one of his countrymen, Bernard Bellador, added to it. And then Charles Augustin de Coulomb established his earth pressure theory in 1776. And the list goes on and on with various tweaks that came of collective ongoing learnings until 1857 with William Rankin's simplified version of Coulomb's theory, ending what is referred to as the first phase of classical soil mechanics. Coulomb also described a mathematical model which described the response of brittle materials to shear stress as well as normal stress, which was then simplified by Christian Otto Moore in the late 19th century. It is still commonly referred to as the Coulomb criterion. With a great deal of focus placed on sand behavior in the mid-1800s, another French engineer, Henry Darcy, then published his study of permeability in sand filters in 1856. Darcy was able to establish the coefficient of permeability of soil, a very useful parameter to this day. The underlying theme to all of these numbers and theories and names and dates, and I've left out a ton of them, is that this has been an iterative process that has been improved upon for centuries as we continue to learn more about the behavior of the earth. What would become known as the oil and gas industry that we do know and love today didn't begin to think about geomechanics until the late 19th century, when Colonel Edward Roberts created what was essentially the first patented frac technology known as a Roberts torpedo. Geomechanics of the present. Known as the father of modern soil geomechanics, Carl Terzaghi became recognized as the leader of a new branch of civil engineering at the time, known as soil mechanics, while serving a lectureship at MIT from 1925 to 1929. He passed at the age of 80 in 1963, having served many large-scale projects and contributing vast amounts of experience to what have since become several fields of knowledge over his lifetime. Modern geomechanics has dozens of applications, ranging from block caving in mines to wellbore stability modeling in oil and gas to permeability enhancement in geothermal exploration. Our need to understand more about the subsurface will keep pace with our pursuit of that higher and higher hanging fruit, pushing us to more technically challenging and operationally dangerous environments all the while. The advent of geophysical logging tools, powerful lab equipment, and seemingly endless computing power have brought us to new levels of geomechanical comprehension. But where do we go from here? We've moved from developing theories to establishing specialty disciplines that can understand them, to pulling rock out of the earth from its deepest depths and inferring what we can from how the rock responds to various acoustic, electric, or radioactive stimulation. But is that it? Or is there more learning to be done? This device represents Integrity Insitu's best effort towards finding more answers. We call it the Insight tool, and our first limited field trial takes place in about 4 months. Large volumes of both practical and theoretical knowledge must be translated from the realm of soils and weak rocks to hard rocks and crystalline structures, no different than what the geomechanics community has been doing for 300 years. So again, I want to reiterate, we've seen, and you all have a lot more experience with this than I do. We've seen the iteration over time of the different theory involved with weak rock, soil mechanics, et cetera, and that needs to continue to evolve. There's going to be new theories, there's going to be new formulas, new technology, and this is part of that. Okay. There's obviously a lot more to all of integrity in situ than showing you a pretty picture of the Insight tool in a graphic. So to really understand who I am and how and why I built integrity in situ, we need to do a bit of a deep dive. I'm going to grab a little sip of coffee. Rule number 1. Without the right support at home, tasks of this magnitude aren't happening, not in my experience. You need to include your family in your challenges and your successes. Be open and honest at all times, and know how to leave everything at the door when you get home. I'm not saying that I do that all the time, but I sure try, and I've gotten a lot better at it. This is my family, obviously. You see my lovely wife, Kristen, and our 4 boys. You got Liam, the big guy, he's in university out of Vancouver Island. Then you've got Felix on the left, Jonas, the blondie, that is a boy. He's just got the baby Thor hair, and then Silas down here in the middle. All rascals. Rule number 2, work harder than anybody else. If you can put in 50% more work than your competition, you'll produce 50% more results. They won't always be pretty, you're right, but they don't have to be. And a lot of people don't get that. You don't have to be right all the time. I've run this tool every time it's gone to the field. I've run forklifts, drill pipe. I've met with dignitaries. I presented at conferences. Whatever it takes, you do it. As a business owner, as the founder. Rule number 3, resolve to suffer. You must accept the fact that there will be bad days. Expect them. Don't hope for them, but expect them. And accept that you will fail, but remember that failing is progress. You will be failing forward. You're going to be scared at times. I certainly was, but this too shall pass. And making sacrifices is an absolute requirement. Making sacrifices is an absolute requirement. So know that it's coming. Because when it arrives, it might be more than you ever thought you could handle. This incident occurred in May of 2015. I'd been in the UK with our prototype design team, and having just fired them, wasn't in a real great space when I got back to Calgary. The 10-hour flight in economy, the stress, recycled air, whatever it was, I ended up with a mystery bug that had me in a self-induced coma for 4 days. This happened about 2 weeks after returning to Calgary. My doctors told my wife that I had a 30% chance of survival. And there is a special kind of fear that comes of waking up with no memory, not being able to see out of one eye, or not knowing if your family is alive or dead. I couldn't work for 2 months. I couldn't drive for 6 months. I did have a full recovery, obviously. But having been through that, developing downhole tools in the midst of a terrible economy or a global pandemic, or fighting with investors, dealing with a hostile government, none of that matters. None of that gets to me. And life does go on. I had no choice but to succeed in my mind. and I was not giving up on my dream. We ended up running our prototype tool 5 times over the next 2 years. This is me on the right running pipe on that rig. We had some successes. We had several failures. I essentially wandered in the desert bankrupt during that entire 2-year span. And so it went. And then I see an email from Saudi Aramco. They'd heard about our technology and wanted to run it. Once we discussed particulars, the decision to build a new tool that could operate at high temperatures and high pressures was made, and we had a new lease on life. Alberta Innovates, who is a local provincial government organization that help with technology development and funding. They stepped up with a sizable grant that helped us with development costs, and I started to build a team. This incredible, brilliant team. Oh no, Kim's picture is missing. That's too bad. This group, as I mentioned, has about 300 years of R&D experience, and oh, okay, there's Kim's picture. I'm very technically savvy, as you can tell. But this group has done some truly amazing things. We'll get into the specifics of the device they're building shortly, but first things first, what followed the incredible technology that exists today, why did I feel compelled to do this? And it's a bit of a long story, so I won't tell the whole thing, so we get a bunch more slides to get through. But to put it bluntly, having personally been a client of those tools and lab processes, they're just not enough. Trying to retrieve core that is suited for mechanical testing isn't always a trivial task, depending on your target. And geophysical tools, or the models that come of them, aren't usually calibrated to the location that you're trying to investigate. And I'm sure you've all seen examples of poor core recovery. And if you did recover the core you expected, it might have been rubblized. You can't mechanically test that in a lab. Okay, so the little blurb on this slide says the traditional mechanical recovery testing is dependent on core recovery. Not anymore. The Insitu tool brings the lab to the reservoir, eliminating the need for geomechanical lab testing of core samples. It's comprised of 4 functionalities, 3 of which are physical mechanical tests of the open hole wellbore wall. Imagine a downhole geomechanics lab. That's exactly what you're looking at here. The mechanical tests include our Shear Head, the Minifrac, and something we call an intelligent packer, which is an instrumented packer. The other functionality is a gamma sonde, which we use to help locate us within the wellbore. Okay, so this is the data list that we expect to see of the Insitu tool. Each and every time we run this device, this upper list is what the tool will be measuring directly every time. We also have numerical and analytical modeling capabilities, which can provide another large, very significant number of geomechanical properties. I don't know if I can change my pointer to, there we go. Okay, so this particular image is showing you pressure meter data. A pressure meter is an instrument that's been around for about 70 years. It came from the civil engineering world. And what you're doing with a pressure meter is you're loading the wellbore wall with force and you're unloading that instrument, allowing that rock to rebound. You run that inflation, the loading and unloading cycle multiple times. And you take this unload reload loop, you put a best fit line through it, and you feed all that information into cavity expansion theory. And this, as I said, has been around since the 1950s. It was originally invented by a fellow named Louis Menard, again, another French engineer. And it provides a massive amount of the information that comes in the tool. The shear head, you're looking at cohesion, friction angle, unconfined compressive strength, Minifrac. Everybody's familiar with Minifrac, also known as a DFIT, minimum in situ stress, permeability, and whatnot. Okay, so the intelligent packer. This is not your grandmother's pressure meter. This instrument can exert 20,000 PSI compared to 3,000 PSI in a conventional pressure meter. It's meant to run in well bores of up to 20,000 pounds of hydrostatic head and temperatures of up to 330 Fahrenheit. So as I was saying on the last slide, think of a traditional packer and now instrument it to measure displacement and also measure force. Displacement in the rock translates to strain. Force translates to stress. So by instrumenting this inflatable packer with 12 individual sensors, we follow the displacement that we create as we inflate the element and load the wellbore wall. With these 12 individual sensors, we are seeing 6 individual planes of travel through the tool into the wellbore wall, and identifying stress anisotropy and stress orientation as well. Now, one hope that I have, it's kind of a long shot, I don't know, depending on the degree of anisotropy and the magnitude of maximum in situ stress, we may actually be able to quantify maximum in situ stress with this instrument, but that remains to be seen. Okay, so this speaks a bit to that background, the different types of pressure meters. This picture shows the loading that happens in the wellbore. The picture on the left is actually our very first intelligent packer on our prototype back in 2016. We ran this on an oil sands well, roughly 600 meters of depth in the Peace River region with coal oil sands. And this is the information that comes out of that instrument. That test, like I said, cavity expansion theory has been knocked around and modified many, many times over the past 70 years by a number of PhDs and civil engineers and geomechanical experts to get it to what it is today. And it's going to continue because we are taking it places it's never been. This slide speaks a bit to cavity expansion theory. There's a bunch of assumptions that we know aren't necessarily accurate in the real world. And all of these things are going to be taken into account as we move forward. Now, this slide speaks to elliptical boreholes. We know that holes don't remain engaged for long, if at all. And the point of this slide is basically to say that we're aware of that effect and that there will be different equations and modeling techniques needed to evaluate those zones. So this is the intelligent packer. From imagination, particularly before 2016 when that shallow prototype was built, to reality now. We have a big crate on a plane right now heading back from the UK, where we were getting a specific section of this instrument fabricated. It'll be back in our hands next week, and we'll begin fitting it to our own equipment and starting some bench testing here in Calgary and sending this guy out to the field with the shear head and communication sonde and gamma module in probably May. The shear head will be going out sooner than that, but the intelligent pack will be right behind it. This picture down here on the right shows a bench test assembly. Basically, anytime we had very specific questions or concerns from the engineering standpoint about how we were going to do some of these things at 20,000 PSI, at 330 Fahrenheit, up to 5,000 meters away, we would build a relatively quick and dirty version of the concept, and the hydraulic power units that are present in each of these functionalities individually, they're all independent systems. We built one that could get spread out on the bench to make sure that some of the valves that we had to devise, custom valves, and the ways that we ramp up our pressures. We're going to work with our overall hydraulic flow paths and accumulation systems, fail safes and whatnot. So this is just an example of some of that bench testing that goes on as we prototyped various aspects. Okay, this is the shear head. The shear head replicates a direct shear box test as well as a scratch test. This image was taken in a barrel that we set up, cored out, sent the core off for lab testing with that shallow prototype. We've got the same thing set up now with a different material in our lab for testing the high pressure Insitu tool shear head. But you can see why we claim that yes, we're reproducing a scratch test. And here's a traditional scratch test here on the right. In the field, there would be a bit of a gap between these various penetration depths so that we're not interfering with the next penetration depth. But what we've got are hydraulic rams with pointed cones on the ends of them that are radially extended from the wall, from the tool at 6 different points, helically oriented around the body of the tool. Those rams are going to penetrate the rock to a depth that we determine, applying normal force. This is where we get into the shear box concept as well. We apply normal force with those radial rams. Once we've penetrated the rock, that entire assembly moves perpendicular to the normal direction, which creates the scratch. So we've gone from applying normal force to shear force, perpendicular to that normal direction. And because we know the depth of penetration in the rock, and we know the geometry of the cone that's penetrating the rock, force over that area equals stress, normal stress and shear stress. And that's how we replicate a direct shear box test. The shallow prototype had 9 rams. The high temperature Insitu tool has 6, simply because of size, space constraints. You have to design things very, very differently when you get to these types of pressures. So this particular instrument is of very high interest to a lot of folks, specifically for the UCS and cohesion and friction angle data. Now, switch this pointer back. There we go. This animation just shows that when you penetrate the rock, that force isn't only being seen, or you're not only affecting the grain material at that steel and rock interface. That force travels into the rock, and accounting for that is part of what's been done here over the past several years. We've literally developed this theory from scratch, which is great because we got the scratch test involved. I like that one. But all of this fancy math that I don't understand, that's definitely not my bailiwick. This was developed by Mehrdad Sultanzadeh, but the original theory and principles on how to actually analyze this data was established by David Yale. And I'm sure many of you know that name. David put together 9 versions of how we analyze this data. What is actually happening to that rock when we run this test? So David provided a fantastic foundation that Mehrdad has since built on, and another fellow, another PhD with a lot of geotechnical background, Sheldon Wang, was also involved in some of those iterations. And this slide is basically, again, intended to show we know that there will be a point in a certain material at a certain pressure when we're moving from one failure type to another. And we will have to figure out how that gets addressed. There's going to be a lot of questions. There's going to be a lot of, like I said, there's going to be new theories. There's going to be new math. There's going to be additional technology that the geomechanics community is going to benefit from. And I want all of you involved in that. Another slide basically showing how you can pull any data you want out of, well, anyway, elastic data out of these tests. And you can use these tests to compare one another and make sure that everything is on the up and up. Here we go. The shear head. It's real. There it is. We've got some updated pictures, but between my phone and my laptop, it's tough to get some of these high, large file size images from one spot to another. I do post quite a bit of this on LinkedIn, but certainly not everything. But here you see the shear head as well, this isn't how it exists today, because today it's in 3 big chunks that are being run through the paces in our shop and headed to the field as soon as our communication sub is fully assembled, which will be probably April type of time frame. What you've got down here on the left is the shear head anchor. When we run the test, because we are moving axially, we don't want anything to react into the drill string. So we actually deploy these 6 slips against the wellbore wall and make sure that nothing below that point is going to move. Those slips apply more force than the radial rams, and this has all been fully assembled and bench tested. I'll see if I can get this little video to play for us. There we go. So it's quick, but I'll start it again, unless I don't get to see the actual slider, which I don't. Sorry about that. That video showed another one of these bench type models of the radial ram section. You know what? I'll just go back a slide and I'll come back. If you look closely, you can see that radial ram extend and then pull back into that body. So again, core engineering questions. This particular challenge had a fair bit of hair on it, so we built a small version of that radial ram body and pressurized it all and cycled it. And that video was actually shot the very first time it was cycled, and the engineers who were building it weren't too enthusiastic about having a bunch of witnesses the first time we did it, but I made them do it anyway. This picture down here on the right shows an indentation in a steel pipe. We took one of our fancy radial rams, which is made of basically a branded alloy that I can't disclose, but it's got an incredibly strong strength rating, tensile strength rating, over 300,000 PSI, I believe. Anyway, we took this radial ram and cycled it 900 times, used it to penetrate the steel and made sure that the ram was okay, which it was. Okay, Minifrac. Pretty straightforward. One thing that makes this interesting is that our overall activation system, the actuation method for these elements for the Minifrac, everything is self-contained. We have our own hydraulic power supply on board for each one of these functionalities. So there's 3 hydraulic power units that go into the inside tool. And that allows us to control some of the different, I guess, functions that have to happen here at depth and at pressure. And that's allowed us to wade into some technologies on the element side, the rubber element side, the packer side, that simply were not available with a mechanically set packer. This system is rated for a differential pressure of 15,000 PSI, and that is game changing. We have yet to finish building this thing, so it's not proven, not by a long shot, but we have got the elements that we figure will work, and the proof's in the pudding, so we're going to find out. Minifrac testing, defit testing, microfrac, everybody's pretty familiar with this. It's been around since the 1930s. Create a fracture, allow that fracture to heal, see how much force it takes to open that fracture. Now this picture is not a pretty one, but this is reality. As you're trying to build these things that have never been built before, you're going to fail, you're going to blow things up, you're going to ruin parts, you're going to spend a lot of money, hurt your schedule, yada, yada. And this is an example of that. This is some of the testing that we had been through with the mechanical hybrid version of our Minifrac elements. Okay, flex joints. Flex joints are basically where you want the tool to bend as you go through a build section into a horizontal well. this tool is not limited to vertical wells. We can deploy on wireline, we can deploy on jointed pipe, we can deploy on coiled tubing. We've recently designed a very high pressure side entry sub that's meant to handle the differential pressures involved with our Minifracs at depth. So that's pretty exciting for us. But anyway, these flex joints, again, meant to take that bending force as you go through a build section into the lateral. And these flex joints are intended to protect the tool from a dog leg of up to 20 degrees, which is pretty bad. Here we go. This is real. This is another version of a benchtop test model, though. This is made of aluminum, so that it was relatively quick to fabricate, cheap, easy to handle in a CNC and on a lathe and whatnot. But we had this version made up, and one of our mechanical engineers, Stephen Trembath here, this is a video, but every time I turn it on, the video turns sideways, so we won't bother. But Stephen got this in his hands and put all of our hydraulic fittings and electrical pass-throughs into the tool and pressurized it to 20,000 PSI, and it held pressure the very first time. Ran hundreds of cycles as well. So the flex joints and the field joint assemblies were a success. Number of applications for this technology. This list is specific to oil and gas, but this is not specific to oil and gas. This is applicable to civil engineering, mining engineering, geothermal exploration, and I'm trying to get into some doors with NASA to take this tool off planet, because right now the Perseverance rover is collecting core samples on Mars, and they're the size of a pencil, and they're meant for different purposes. But if geomechanical properties are something that NASA starts to think about when they get closer to putting people on the planet of Mars, I sure as heck hope that they're not going to try to capture core and ferry it back to Earth. So anyway, when it comes to oil and gas applications, obviously, if you can physically capture rock strength and stress properties from within your lateral, you can optimize your frac. The same can be said with caprock integrity, wellbore stability. Anytime you need that information, why would you not capture it in situ? All of the data is seen at surface in real time as well, by the way. When it comes to optimizing fracs, if you're going to use 5% less water, you now have a clean tech. If you're using 5% fewer chemicals, less proppant, fewer vehicles on the road, reducing emissions, you now have a clean tech. It's good to have friends, and we have a few. I definitely want your logos on this slide the next time we present. But as you can see, we've got some great feedback from a lot of folks around the industry. Okay. As said by Carl Terzaghi himself, all the modest achievements, which I have to my credit, can be described by a simple formula. Guided by common sense and casual observations, I recognized weak points in traditional procedures and tried to make them less weak. Sometimes I failed, but usually I succeeded. That is my goal, and that is the end of the presentation.
Thank you, Cory.
You're welcome.
That was really inspiring, actually.
Thank you.
We do have a few questions, and you know, they're few enough that if people want to unmute and ask, then we can do that. But let's start with the chat. And I lost it. I think Tom Doe had a question, and he was wondering about the diameter of the tool.
The current design is 5 3/8, and that is specific to Aramco's request. Aramco, as I said on one slide there, are involved in the R&D and development costs, supporting those development costs for the Insight tool. And we have 3 test wells lined up with Aramco. And once the Insight tool has been tested locally, whether it's Alberta or Texas, once that's been done, the tool goes over to the Middle East. and working on a variety of North American sizes is definitely something we have to start having conversations about.
Very good. And Eddie Siebert's, Ed's question is actually a good one. What's your ground truth? I mean, can you comment on direct comparisons between your tools results and lab data from co-located core or something similar?
Yep, definitely. The prototype was tested against direct shear box testing. The Shearhead was tested against direct shear box testing, but we didn't take it any further than that simply because of budgetary constraints. We did capture core on test wells, but that would be a well where we had some other issue and we didn't get any data out of the prototype. So the early day ground testing, or sorry, ground truthing was not successful. The Insitu tool, however, we've got a full suite of geomechanical tests happening right now with MetaRock in Houston, thanks to our friends down there. And yeah, we'll be comparing everything under the sun to those cores, and they're not going to match. They're not apples to apples, those comparisons, but it'll be an excellent indication as to where we are in the ballpark, and go from there.
And the next question, Cory, is from Professor Solomon, and he's wondering if the tool can allow constant flowback rate in the Microfrac application.
100%.
So your downhole pump can operate in both directions.
Well, the downhole pump is only for the hydraulic power unit. We pump from surface.
I see. Okay.
Yes.
Okay.
Can I add something to it?
Please.
How constant is the flowback rate that you can control? Can you go down to a few gallons per minute and you keep it constant?
Liters per minute, yes. It's controlled electrically. Yeah.
You may not be aware of, but we have done applications like this many years ago, except we took it even to the field as an application, but somehow it got abandoned by oil companies.
You're speaking about the flowback control specifically, Professor?
No, I'm speaking about the Microfrac, including flowback manifold. And just to add something to it, we just developed a complete solution for the problem of pump and flowback, both analytical and numerical solutions. And we're having problems of getting data, field data to analyze beside the data that we produced 30 years ago. So we had to go back and digitize those data. So I'm glad to see what you're doing.
Thank you. Oh, we should get together on how to handle that data.
Anytime.
Okay.
Thank
Very
you.
nice. And Salazar is wondering what's the typical formation or lithology that this tool, well, it says has been used on, but maybe you just talk about that in general.
Yeah, so we're definitely targeting weak rocks and hard rocks, sandstone, shale, limestone, conglomerate, anything under the sun. At some point, we're gonna have to work with granite as well, because that's where geothermal action is at. But we'll see what kind of forces are required for that.
John, can I make a comment? This is
Ali, I'd be disappointed if you didn't.
You know, as I listen to your presentation, the thought that comes to my mind is actually using this tool in a well bore which is already lined and cemented with casing in it. And you can put this tool in it and then determine the movements in the well bore caused by activities in adjacent wells during fracturing operations. Basically, this is it could be an extension of this sealed well bore pressure monitoring. If you can measure the deformation of the well bore when somebody in adjacent well is fracturing, you should be able to determine quite a bit about the properties of the formation and properties of the fracture. Has this been, it appears to me that's possible. Has this been in a part of your plan?
It hasn't been investigated. And this is one of the things I love about these conversations, because you all have the knowledge. I don't have the geomechanical knowledge to know the 50,000 applications we can take this tool to. So thank you for bringing that up. When it comes to observing movement in the borehole as a neighboring well, a child or a parent well is being fracked, the resolution required.
No, it's primarily in infill, not child and
Okay. Okay. Well, the point still holds true though. I don't know what kind of resolution the instrumentation would require. We can measure a movement to within 1,000th of an inch, but depending on the coupling going on between the borehole and the cement sheath and the casing, would you actually see anything? I don't know. I'm obviously happy to try, but no, that'd be interesting to look at for sure.
Actual measurements have shown that you can see pressure changes in the wellbore, maybe sometimes as high as a couple of psi.
Oh, well.
This is pressure change in the wellbore that, of course, your tool can measure without any difficulty. That's trivial for your tool.
Were those obtained with fiber optics?
Yeah, that is just regular pressure gauge.
Okay.
And the advantage your tool offers is that you can also determine the local deformation of the wellbore, which allows you to determine where in the well these deformations are taking place.
Mm-hmm. As long as you're stationed properly. This is these are static measurements, right? So yeah.
But if you can move your tool, you can take these measurements multiple times.
Yep.
Up and down the wellbore and determine the location.
Absolutely.
Yeah, that's an interesting possibility suggested there. We do have a couple more questions. Romain is wondering, what is the range of radial deformation that you can tolerate, the OD of the tool versus the borehole diameter?
Yeah, unfortunately, it is relatively limited. We can see out with meaningful data, expected meaningful data out to about 6 1/4 from that 5 3/8. So about a 1/2 inch deformation on each side from the gauge of the tool.
Okay. And then Luke Fresh, Luke, appreciate your presentation, and in your presentation you highlighted some of the harshest negatives of entrepreneurship in geomechanics. But what were some of your favorite parts of this career path? Now, there's a question you don't often get.
Yeah, no, that's a great question. Thank you for asking it. Honestly, one of them is what I alluded to earlier, these conversations with folks like yourselves. I have a lot of respect for all these names that I see on the call, and it's been an absolute pleasure and honor to rub elbows with everybody for the past 8 years. I've learned a tremendous amount, but the relationships that come of business and building a team, they're invaluable to me. And obviously you get to do a lot of things you wouldn't normally do. I've been in some pretty interesting places that I normally wouldn't have had access to because of the nature of the conversations we're having. And I don't know, there's a certain, I guess, joy that comes with creating, but at the same time, until the job is done, I won't be satisfied.
Yeah, fair enough. Alexei Savitsky, once again, he also appreciates the motivational story. And his question is, the scratch test interpretation requires very tight control of the groove depth. Since it can be controlled downhole, how do you interpret the scratch data? And have you tried to compare with core scratch data?
We haven't compared it to core scratch data, but we do have scratch tests being done now that we will be comparing to within the next few weeks. So there'll be information on that right away. Now, the way that we control that depth is by hydraulically locking that system when it's in motion. We run that penetration cycle multiple times, so you do get multiple penetration depths. And we could run the cycle 10 different times if we wanted to. The test takes about 7 minutes. So it's very simple to, I guess, double check what's happening if you think that maybe you've got a borehole issue or something wasn't quite as expected mechanically. You could rerun the test quite readily. But locking the system hydraulically is how we control that penetration depth to the degree that we can do so.
Thanks. Dan Moose had a question, and Dan was wondering logistically, how long does it take? How long does each measurement take, and how many repeats do you typically use or consider necessary to get consistent results?
Sure. So the shear head, as I just said, is about 7 minutes per test. The intelligent packer, anywhere from 30 to 45 minutes. Minifrac, on a good day, in a a manual flowback cycle type of a scenario, you're looking at about 4 hours minimum. So we generally tell operators to give us 24 hours in the borehole. And with 24 hours, you could run the shear head 20 times, run the intelligent packer 6 or 7 times, and then run a few mini fracs as well, whether you're in the lateral or whether you're in the vertical coming out of the hole. So needing to be on station for anywhere from 7 minutes to 4 hours, it's really going to depend on what the operator is after. Everybody's got different preferences for which aspect of the data they see as most valuable. And the test design is certainly predicated by what the client wants.
John, can I just another question? What would you do if the tool gets stuck as a result of ground movement? I mean, I don't mean to be negative, but that's a question that any operator would be, concerned about.
Yeah, 100%. And we have we have the conversation all the time. There's a ton of features built into the tool to allow us to get unstuck. But if that happens, being on pipe is your best defense. You can pull with 400,000+ pounds of force to get this thing out of the ground. And if worse came to worse, then there's no way it's going to come out. Then you would simply rotate off, and you'd have to, well, you could attempt spearing, but you're not going to get any more force out of the spearing fishing operation than you are out of the actual jointed pipe, I wouldn't think. But yeah, at the end of the day, you might have to drill it out.
That's a fair answer. We have another question about the length to the diameter ratio of the packer used for the pressure meter testing. And have you looked at corrections for the finite length to diameter ratio?
Yep. And this is all part of that black box of the cavity expansion theory and those ratios. And the original pressure meter design involved fixed end packers. And that's just not happening at 20,000 PSI. So being able to modify that ratio on the fly and incorporate that into the math is part of what we need to do. And we have another question. It's either from Jean or Jean. I apologize, I don't know which. Could you comment on the fluids used to inflate the packers? Is it water? No, it's straight up hydraulic oil. Yeah, we have our own internal supply of hydraulic oil for each hydraulic power unit. So the shear head has its own, intelligent packer has its own, and the Minifrac section has its own hydraulic power unit that is strictly a hydraulic reservoir, essentially, with some a lot of things going on for safety purposes, fail safes, things like that. And that hydraulic oil is what we use to inflate those elements.
Cory, that's all the questions I have in the chat, but we'll just get people a minute here in case they want to go extemporaneously.
John, can I ask a question here? Cory, first of all, it's a great presentation. I enjoyed the background, and you must have thought many times, why in the world did I tackle such a complicated instrument?
Smart enough to second guess those motivations, dude.
And with all the complications, it's very easy to throw rocks at it and say, hey, what about this and that? And indeed, and it's true, there are a lot of questions here, but one of the big ones that any kind of a borehole measurement is making, whether it's a logging tool or whatever, quite a few of the measurements are near the wellbore wall. They're close by. And so that zone has been damaged probably due to drilling. And so I guess there's kind of no way around that is any kind of a measurement like that's right near the wellbore, like an indentation or scratch test will suffer from that it has near wellbore. But I really commend you. I'm assuming that every time you put one in the hole, when you do and you bring it out, it's like one of your family members. Am I going to lose a family member? Am I going to lose this tool? But congratulations on the fine work. And I think it remains to be seen as whether this complex reading can really be practical and catch on. But congratulations to you all for doing it and trying it.
Yeah, thank you.
We do have a couple more that came up on chat. And Tosin is interested, can the shear heads be operated independently?
Absolutely. Every functionality can be run independently of any other function. And you could deploy just the shear head if you wanted to. You could run just the shear head on wireline if you wanted to.
John, can I ask a question?
By all means, Zhang.
Okay. Yes, Cory, thank you very much for the wonderful presentation. So do you select which section you are going to test? And for example, if you have this horizontal wells, maybe you have some shear section, you have some limestone or sandstone. So how do you select the section you are going to test?
Well, we do have a gamma sound on board that'll help differentiate exactly what we're looking at. Beyond that, we will be relying on the operator to tell us this is what they know is there. We've talked about adding, well, my team hasn't, but I brought it up. They don't like me bringing up adding more things to this already very complex instrument. But at the end of the day, maybe we've got a couple more functionalities on board that'll give us some advanced petrophysical logging capabilities to acquire more data through whether it's logging or maybe it's fluid sampling, or maybe it's something like even a monopole sonic would be helpful. So yeah, it'll be with our own gamma sound to get back to your original question and whatever other information the operator can provide.
Thank you.
You're welcome.
The only other final comment in the chat is from Gong Pan, and he appreciates great talk and an inspiring story.
Thank you.
Anyone else before we let Cory get back to getting this tool in the ground? Well, thank you, everyone. And Cory, thank you. We really appreciated it. And we'll see everyone in a couple of weeks with our next presenter. But Cory, thank you. Great talk.
Thank you so much. You're welcome. And I really appreciate the opportunity to speak with y'all. So thanks very much. And feel free to reach out anytime. I'm on LinkedIn. I'm not hard to find. My phone number is out there, my email address as well. So don't be shy.
Yeah, Cory, that was really nice.
Thank you.
So you figure May for your field trial?
Yep.
Well, you'll have to come back and tell us how it went.
Yeah, definitely. And I'm not afraid to share our failures, so that's no problem. I'll gladly do that.
No, we're remaining optimistic, man.
Yeah. Oh, I'm very optimistic too.
That's your fourth rule. That's got to be your fourth rule.
Yeah, stay positive. Yeah, for sure. There's a lot of that kind of stuff that has to go on. Absolutely. Yeah. But comparing this to the first go around, John, there's one similarity, and that is the concept sure. Of the shear head, the intelligent packer, the Minifrac. Beyond that, nothing is the same. Yeah. This team has built a downhole tool meant to operate in very harsh conditions. And there's a ton of oil and gas specific experience on this team compared to the first go around. Everything was farmed out initially, and that was a bad idea, but I didn't know any better. Sure. You know, it's one of the many times I stepped in it, but I learned from that mistake and built a really fantastic team here in Calgary that's getting it done. So yeah, I'm excited and optimistic.
Well, we wish you great success on this. It was a fascinating tool.
Awesome. Yeah.
And
Thanks so much. Are you able to send me this recording, John?
I
on
can send you
Dropbox
the,
or something?
I can send you the recording. I don't know whether I can send you the chat. I know there's a way to do that, but I don't know whether I
That's fine.
activated it. I should be able to send you a list of participants too.
Okay, wonderful. Thank you so much. Okay, well, keep in
Very
touch
good.
and
Okay,
talk soon.
okay, see ya. Bye-bye.